Good morning, team. Today we will talk about how we check if our jacket structure can survive an earthquake. Today we will talk about how we check our jacket structure can survive an earthquake. So, what exactly is a jacket structure? Is it like a coat of the for the platform? No, not quite. A jacket structure is a steel frame work that supports the offshore platform above the sea. It's like the legs of a tall stool running in water. Okay, what if the stool starts shaking during an earthquake? Will it fall? That's what we must make sure that it doesn't do. We perform seismic analysis to check that. How do we know how strong that earthquake will be? How do we know how strong that earthquake will be? Because we design for two levels, two earthquake levels. One is extreme level earthquake, another one is abnormal level earthquake. So AL is a big one. This is a big one, and ALE is even bigger. Exactly. Under LE, the structures would mostly stay elastic. So these are like under extreme earthquake, the structures would say mostly elastic. Structures would say mostly elastic. Under ALE, it may bend a little, but must not collapse. It may bend a little, but must not collapse. So which software do we use for all this? Is it SAX? Yes, we use SAX with dynamic for modes, dynamic response for earthquake reactions, and this post and joint for checking the members and joints. How many natural frequencies do we check? 10? Usually take 20, even more than that, maybe 30, 40 like that, to make sure all the significant vibrations are included. All the significant vibrations are included. What is a mode anyway? Like a music mode. What is a mode anyway? Not quite. A mode is a way that structure moves or vibrates. Mode is a way that is the way the structure moves or vibrates. Think of how tall a building sways in different patterns. Think of how a tall building sways in different patterns. Each is a mode shape. Tall building can sway in different shapes, right? Tall building sways in different patterns. So each is a mode shape. It can bend like this or it can bend like this. So it can sway like this, it can sway like this. So each in a different patterns, each is a mode shape. And what about damping? I heard the term, but I'm not sure what it means. Damping means energy loss. It's like a suburb success in a car. For steel structure platforms, steel obstacle platforms, we usually take 5% damping. How do we combine the vibrations in X, Y, Z directions? How do we combine the vibrations in X, Y, Z? We use two mathematical tricks. One is CQC, complete body combination for modes, another is RSS for the directions. That sounds complicated. Why don't we just add them directly? Why don't we just add them directly? Because earthquakes don't shake equally in all directions at the same time. At the same time, it's not going to shake equally in all directions. That's why they combine differently. So the CQC and SRS handle that properly. What about the piles under the jacket? Do they also feel the earthquake? Do they also feel the earthquake? Yes, absolutely. We model them as equivalent pile step and also run a single pile checks to make sure they stay safe under ALE loads. They should stay safe under ALE loads. If the stress in the members becomes too high, what if the stress in the member becomes too high? We can increase allowable stress by 70% for members and 60% for joints during earthquake conditions. As per API-RP2A. So whatever the problem shakes too much, like that moves sideways a lot, we limit the maximum deflection, maximum horizontal deflection to h by 200 h is the tolerable structure. How do we know everything is okay at the end? How do you know everything is okay at the end? We check the unity check ratios. If they are less than 1, the structure is safe. So what did we find in our analysis? All member joint used by users are less than 1, deflections are within limits, structure is safe for both. That's safe for both ELE and ALE. So in short, it won't fall, right? It will shake, but it won't break. It's going to shake, but it's not going to break. That's our relief. Can you call it that simple? So, morning everyone. Today we are diving into something really that shakes things up. Earthquake analysis for offshore structures. Earthquakes out at sea. Do we even get those? Do we even get those? Yes. Seabed can shake just as well as the land. So tell me, what do we call the structure that supports our platform? The platform is close but not quite. It's called jacket. Think of it as a giant steel frame holding the top side steady above the waves. So it's like a scaffolding for the ocean. Exactly that. Except the scaffolding weighs thousands of tons, must stay upright when the earthquake moves beneath it. When the earth moves beneath it. So how do we even start checking something like that? Surely we can't just check it by hand. No, thankfully not. We use a software package called SAX. Even ever heard of dynamic response joint can? I have played around with Dynapack before. That's for extracting the natural frequencies, isn't it? Dynapack, that's for extracting the natural frequencies, isn't it? Spot on. Now tell me, what do you think about the natural frequency? What do you think a natural frequency is? What do you think a natural frequency is? Something about how fast the structure vibrates naturally. That's something about how fast the structure vibrates naturally. That's something about how fast the structure vibrates naturally. Okay, precisely. Every structure has a rhythm of its own. Every structure has a rhythm of its own. Too much excitement, they are wrong rhythm, and it dances itself off to bits. So we calculate first 20 mode shapes to see how our jacket wants to move. So we calculate first 20 modes to see how our jacket wants to move. 20, isn't that a bit much? Isn't that a bit much? Would you rather miss one important vibration mode and let the whole thing twist off its points? Better safe than sorry, right? So you mentioned ALE and ELE earlier. What exactly are they? What exactly are they? The two key players. ELE stands for earthquake serious but manageable. That's serious but manageable. ALE is abnormal earthquake, rarer, stronger, downright unpleasant. So we design for both. Indeed, the jacket must stay elastic during ALE. During ALE, it might bend a little but must not collapse. How do we know how strong these earthquakes are? Do we just guess? No guessing is running. We use the API response spectrum, which tells us the expected accelerations for different frequencies. So API response spectrum that tells us expected accelerations for the different frequencies. So accelerations for different frequencies, and we apply it in three directions, all three directions, right? Exactly. The full spectrum along x and y and half along z. Do you know why half vertically? Do you know? Do you know why half vertically? Do you know why half vertically? Do you know why half vertically? Because the ground does not jump up and down as much it shakes sideways. Because the ground does not jump up and down as much it shakes sideways. That's it. Horizontal shaking usually dominates the offshore seismic motion. So once we know how it shakes, what's next? We run the response analysis and combine results. Do you remember CQC assessment? CQC for model combinations versus combining rights. You have been reading your manuals. Why can't we just add everything together? Why can't we just add everything together? Because seismic doesn't loads don't all peak at the same time. They don't all peak at the same time. It's like a waves in a bathtub. They overlap and interfere. Frequencies capture the realistically. How do we include the damping? We assume 5% damping as well. Think of it as a friction that calms the vibration down. Think of it as friction that calms down. Friction that calms down vibrations. That calms vibrations down. Without damping, our structure would wobble forever. Without damping, our structure would wobble forever, and that's not ideal for sleeping offshore workers. So what about the materials? Do they affect the results much? Absolutely. Steel grade, yield strength, corrosion allowance, all feed into the model. We also include the mangrove water depth, even geotechnical data from the soil. So we are basically modeling the entire ocean and seabed, more or less, just without this. What about the piles? Do they move with the jacket? Yes, do they move with the jacket? We model equivalent pile stuffs to represent the pile soil interaction for dynamics, and then we do single pile checks to make sure that each leg is strong enough. Make sure each pile is strong enough. What if one pile fails? Then you will see something headache redesign in order. Then you will see me with a headache. But seriously, the analysis ensures all piles have this factor of safety. That's much more than one, even on reality. How do we check whether the structure pauses or fails? How do we check whether structure pauses or fails? We use the unity check ratio. If it's less than 1, the member or joint is safe. If it's more than 1, then it's back to the drawing board. Literally, we would resize either resize the member or revise the loads. We would Either resize them or revise the whatever the level stress. Can we increase it for earthquake loads? Whatever the level stress, can we increase it for earthquake loads? Good thinking, yes. We allow a 70% increase for members and 60% for joints under yearly conditions. And deflection limits, do we have any? Deflection limits, do we have any? Yes, maximum horizontal deflection should be less than h by over 200. So if the jack is 60 meters tall, the top should move less than 0.3 meters sideways. That's quite tight, isn't it? That's quite tight, isn't it? It is, but remember the people in pipelines are on top. They prefer not to sway like they are on the fairground, right? So what did the analysis say about our jacket? It behaved beautifully. What did the analysis say about our jacket? What did the analysis say about our jacket? It behaved beautifully. All member and joint ratios were below 1, deflections within limits, and piles well within capacity. So it will survive both ELE and ALE. Indeed, it will shake, sway, grumble a bit, but it won't fall. It will shake, sway, and grumble a bit, but it won't fall. And the key takeaway: design with codes, analyze with logic. Always ask what if before the C decides to test your work. Design, analyze, question everything. Got it, son. So may I ask you, do you ever stop worrying about your structure? Never completely. An engineer who stops asking questions stops improving. Engineer who stops asking questions stops improving. Then one more question. If the platform would talk, what would it say during an earthquake? It would probably say, I'm trembling, I'm stranding, thanks to you a lot, but I'm stranding. Morning everyone, ready to talk about the jacket structure? Honestly, why do we call it a jacket? It's not exactly something you wear. Good question already. It wraps around the piles and holds the deck. It wraps around the piles and holds the deck, just like a jacket keeps you upright and tidy. Does it really move during an earthquake? Though I thought the sea would calm it down. Sea is quiet most days, but when the seabed shakes, the jacket feels every wobble. That's why we model it so carefully. So we are basically designing it to dance but not to topple. Exactly, graceful dancing only, none of that collapsing. So these earthquakes, do we use real ones or pretend ones? We use design spectra from APRP to a code. Very official pretend ones. Two types, ELE and ALE. They sound like cousins in a way. It is extreme level earthquake, serious but survivable. Abnormal level earthquake, but rarer, nastier, but the platform must still stand. What happens if you only designed for ELE and skip ELE? Then one day if an abnormal one comes, you will have a very abnormal problem and call from the client 3 in the morning. So we open sacks. Which module first? Start with in-place model, done for seismic work, add dynamics bit, masses, damping and response spectra. On the piles, are they fully modeled? Not at first, we replace them with equivalent pile steps, or later we do a single pile check for each leg. So what if the soils suffer on one side? What if the soils suffer on one side? Won't the piles bend differently? Won't the piles bend differently? Excellent thinking. That's why we use a site-specific geotechnical data and different stiffness for each location. Also use the site-specific geotechnical different stiffness for each location. So do we take that off before analyzing? We include it. Every millimeter matters when the earth decides to dance. How do we know how fast the platform likes to shake? How do you know how fast the platform likes to shake? That's the natural frequency. We extract first 20 using the dyne pack. Each one shows a different way the structure can vibrate. Each one shows the different way the structure can vibrate. 20 seems excessive. Would you rather stop at 10 and miss the mode? Actually causes the failure. Engineering is costliest profession. Damping 5% is spot on. 5% critical damping for seasons. It's like cushion that keeps the vibration civilized. So when we combine results, why do we use CQC instead of just adding them? Because modes don't peak together. CQC components handles the phase differences, so you don't peak together. So that handles the phase differences. Then we use SRSs to combine the directions. So we square, add, then take root. That sounds like. Do we include all operational loads? That live operational loads with contingencies. The idea is to capture the real mass of the platform. What about the hydrostatic press and buoyancy? Both include the static case. The sea helps little, but we never rely on kindness from another nature.